Hello and welcome to my online presentation for simple harmonic motion. My name is Daniel Caguiat and this is chapter 15 in your text. Okay, about simple harmonic motion. As per the definition, this is periodic motion, or in other words, a motion that repeats itself in time. And the acceleration associated with this motion is directed towards some equilibrium point. In other words, the direction of acceleration is constantly changing, and it's always pointing toward a particular point on the x-axis. We're going to see what that is. So periodic motion can sometimes take the form of a sine or a cosine oscillation. So the equation shown on the right, x of t is equal to a cosine omega t, is the actual equation of the graph shown, x versus time graph. And the a denotes amplitude, or the maximum x position. So in this case it's 0.1 meters, as shown on the graph, the top of the wave peak. So a is the amplitude, and then the cosine omega t is the oscillating or periodic function. So in order to derive equations of motion for this simple harmonic motion system, we're going to use a mass spring system. And we're going to see that this system behaves under the equations associated with simple harmonic motion. So the idea here is we're dealing with an ideal spring, meaning that there's no loss in heat. You can imagine if a spring is moving back and forth, it may generate friction, heat, or permanently deform, and then all of a sudden the spring constant changes because the spring is stretched permanently. We're going to assume that none of that occurs, that we have a perfect spring, an ideal spring. And so the equation of Hooke's law, which is force is equal to kx, holds for this case. We're also going to assume that it's a frictionless surface that the mass moves along, so that we don't have any loss in friction, and we don't have any air drag associated with the mass moving through space. Another key point is we're going to assume that the spring is massless, meaning that the spring mass itself does not contribute to the Newton's law equations, which is what we're going to use. Here shown also is the direction of acceleration, which is along the positive x direction, and the x-axis. So what we want to do is we want to develop an equation that looks like a function of the spring constant and the mass. And so we'll work through the next few slides doing that. Okay, and so the way we do this is we get this system started in motion by stretching the spring from some x equal to 0 point to some value x. Okay, so by doing that, then we release the spring. The spring is going to obviously pull back due to Hooke's law and exert a force on this mass. And so we can kind of guess what's going to happen. Once we release this mass, it's going to move back and forth. And you can imagine that it's going to move back and forth about that dotted line, which is the equilibrium rest point, right? And so the equilibrium point of x equal to 0 is the final resting point of this system if it were to die down. But in this case, we're going to assume that it does not die down because there's no reason for it to. There's no resistance force. There's nothing stopping the mass from moving back and forth. There's no energy being lost to the surroundings. And so you can imagine that this mass is going to always end up at the same maximum x position, the same minimum x position, and just oscillate or move back and forth. And so if you can imagine, this is sweeping out a wave function in time, back and forth, up and down motion. So you can kind of equate this motion with the graph that I showed on the previous slide so that it makes sense mathematically. So let's do this then. We'll go through all the equations and see what we come up with. So we're going to look at a free body diagram, which is what we've been doing. Typically one of the first things you're going to do in Newton's law problems is draw a free body diagram and then apply Newton's second law. So to do that, we replace the mass with a free body diagram. So we have normal force acting upward, gravity acting downward. These two forces are going to cancel each other unless the mass is accelerating in the upward direction, and we're assuming that it's not. Okay, and then the other thing is we have a spring force acting on this mass. And so moving forward, we can break up the vector equation into an x equation and a y equation. We don't care about the y forces because they're going to end up being 0, and we're not dealing with friction, so we don't really need to know what the normal force is. So all we care about is the x portion of this equation. And so the sum of the forces in the x direction gives us mass times acceleration x. But we only have the spring force acting, and we know based on our free body diagram, when we stretch the spring force is pointing in the negative x direction as shown. So we have negative F spring is equal to ma. Now, if we look at this equation, and we can plug in the spring force due to Hooke's law, and so that's what we're going to do next. So by Hooke's law, we've got negative kx is equal to ma. Let's see if this makes sense. So what that means is this: if x is positive, acceleration is in the negative direction because we have negative kx is equal to ma. So that means that acceleration is negative because mass can't be negative. And so if the spring is stretched, we've got negative acceleration, or acceleration toward the center point. And if the spring is compressed, at that point x is negative, and so we've got negative k times a negative x, which is a positive quantity. In that case, acceleration is going to be positive or toward this equilibrium center point again. So this seems like this equation makes sense for what we're trying to do. And so we can rewrite the acceleration term as a second derivative. We've done this starting in chapter 2, where it's dx dt gives us our velocity, and dv dt, or the second derivative of x, gives us our acceleration. So plugging that in, we get the equation shown. And then we can rearrange this equation by bringing the negative kx term to the right, and then basically inverting the whole equation. So we're left with an equation that has a second derivative in it, and it also has an x. And this is a special type of equation. Odds are you haven't seen an equation like this. At least I can guarantee that you haven't seen it in my class. You may have seen it if you've already taken some of the calculus classes. But this is called a differential equation. And the reason it's called a differential equation is because it has differentials in it. It's got the derivative of x, it's got an x in it. And you're not required to really understand how to solve these in this class, but I'm going to take you through the solution of this problem. And so in order to do that, we need to use this differential equation. So this is just very basic differential equation math. So we take the original differential equation and we're going to analyze it. So this equation is a homogeneous meaning the right-hand side is equal to 0 and not some constant or some function. Second order, meaning the highest derivative shown in the equation is a second order derivative. Linear, because we don't have sines and cosines in the actual equation as coefficients of the derivative or a coefficient of the x or anything like that. So it's linear differential equation. And it's got constant coefficients, meaning that the terms that are being multiplied by the derivative and the x term are constants. We know mass is constant and k is constant for any mass spring system. So this is a homogeneous second order linear differential equation with constant coefficients. When you take differential equations, if you have to take that course, you're going to see this quite a bit. So these type of equations, they can have sine and cosine solutions to them. And this is great because we have already kind of like assumed that our system is going to move in the shape of a sine or a cosine curve. So we're going to try the equation that I showed earlier, which is a cosine omega t. So I'd like to talk about what the different parts of this equation are so that you understand a little bit better what the meaning of these terms are. So first of all, we've got position as a function of time. We've all seen that, x of t. The capital A is a constant, which is maximum amplitude, maximum displacement, which is called amplitude. And so this is basically the 0.1 that we showed on the graph, or it's where do we stretch the spring to? That point will be our amplitude at that point for the rest of the motion. And then we've got the cosine omega t term, which is an oscillating function or a periodic function. And the omega is the angular frequency. We've dealt with omega already, angular speed. This is the exact same term. But now we're dealing with an oscillator rather than just a pure circular motion. So what we're going to do is we're going to label these equations, equation 1, which is our differential equation, and equation 2, which is our potential solution. Okay, we need to see if this solution is going to work for x. And we're going to take derivatives of equation 2 so that we can plug it into equation 1. So we're going to need a second derivative, and we already have the x term itself, and then k and m are just constants. So taking the first derivative of x with respect to time, using the chain rule, the omega, which is inside of the cosine term, comes out as a constant, and the derivative of the cosine x is equal to negative sine x, and so derivative of cosine omega t is negative omega sine omega t, and so I plug that in and we get equation 3. So that's just by the chain rule. If you need to review this, you can take a look at your Calc 1 book, and there's examples of how to do this type of chain rule. So now what we're going to do is the chain rule on the dx dt in order to get the second derivative with respect to time. And so that's going to end up giving us an omega squared term. Derivative of sine is cosine, and so we're left with the equation 4 shown. So now we have the two equations we need. One important note before we move forward is we've got x as a function of time now, we've got dx dt as a function of time, and we've got second derivative of x with respect to time as a function of time. What are these terms? Well, dx dt is the velocity of the mass that's moving, and second derivative is the acceleration of the moving mass. And so always go back to the original problem statement if you start getting kind of confused on what we're doing. Remember, we're dealing with a mass that's moving back and forth attached to a spring. Okay, so we're dealing with the x position of that mass, the velocity of the mass, and the acceleration. So these are the equations. So we're going to use these later. First, though, we need to plug them into equation 1 and see if the result makes sense. So here's the two equations that we need. And what we're going to do is we're going to plug those equations in to the original differential equation. So let's do that. Plugging in gives this equation. And we can see that we've got an a cosine omega t in both of these terms. So if we were to divide left and right hand side of this equation by a cosine omega t, we can cancel those terms out. So the final, not the final equation, but the resulting equation after we cancel a cosine omega t is this equation, which has, constants and omega squared. So if we rearrange this, we get that omega is equal to the square root of k over m. Now we know k is constant, positive, and mass is also a positive constant. So we know that omega is going to be a positive constant in this case. And so what is omega? Omega was our angular frequency or angular speed of motion for this mass. So as long as omega is defined like this, we can see that our solution works, and so this is a valid solution for the motion of the mass spring system. So here's the complete description of motion for the mass spring system. First of all, we've got position versus time is a cosine omega t, whatever the amplitude is, whatever the omega is, where omega is the square root of k over m. So you can design your own mass spring system to have whatever frequency you like it to have based on the spring constant and the mass that's doing the oscillating. So this graph below shows the motion of such a system. And as you can see, if we let time equal 0, we're going to get the maximum point, which is a times cosine of 0, which is 1. And so this motion starts out at the amplitude of 0.1 and then continues onward as time goes by. So what I'd like you to do is look at this graph and see how, as the graph moves up and down, you can picture the mass moving side to side. And that's really what's happening here. So the mass starts out at 0.1, and then in some amount of time it moves all the way and starts to get to the equilibrium 0 point, and then it moves inward, so x becomes negative. So in other words, the mass is compressing the spring at that point. And then the spring starts pushing back on the mass. And so we can see at time equal to about 0.1 seconds, the force of the spring starts moving the mass the opposite direction. And so we can see that the mass is now moving toward the equilibrium point again, crosses the equilibrium point because it has some speed now associated with it, kinetic energy associated with it, and it becomes positive again. So then we're looking at mass stretching the spring due to the inertia of the mass. And then at that point, eventually the mass reaches the maximum position of 0.1 again, and the whole process resumes. So one complete cycle, or one complete revolution of this system, is from from time equal to 0 all the way through to time equal 0.2, and then the process repeats itself, which is the case with simple harmonic motion. So if this is a lot to review, please take time, watch this presentation or parts of the presentation as much as you need to understand what's going on. So here are our velocity and our acceleration terms for this system. Using the equations that I showed earlier, we have the complete description of the mass spring system in simple harmonic motion. And again, the system is not a real system, because in a real system we've got resistances, we've got friction, we've got air resistance, we've got losses in heat and friction in the spring itself, and then the system is not going to continue oscillating. It's going to die out. And you can imagine that that would be the case. But, you know, there's other additions to the equation that can account for the resistance and the what's called damping. So if you're interested in those things, or learning going forward, you can look further into the chapter and find damping and see how that works. But all I care about for this course and the purposes of our final exam and things like that, the only thing I'm going to cover is simple harmonic motion with no damping. Okay, so a little bit more on angular frequency. So we call this the natural angular frequency, omega. And it's basically if you have no outside force driving the system, you stretch the spring and you let it go, the system is going to oscillate naturally at this omega, which is called the natural frequency in radians per second. And now we're going to define natural frequency in terms of hertz, or cycles per second, and that would be lowercase f, which is how many wave peaks pass by a certain point every second, and that's calculated as omega over 2 pi. So this will make sense later how we got that, but looking at units, omega has units of radians per second, and there's 2 pi radians per cycle, so you can see how we're going to get cycles per second using conversion factors. In this case, frequency refers to how often the mass passes by the maximum point. So you can think about it that way. And we can see clearly that that's every 0.2 seconds, so cycles per second will be 1 over that 0.2. We also call cycles revolutions. So one complete revolution is what we talked about earlier, whereas the mass starts at the maximum point, moves through, compresses the spring pushes back on it and drives it forward again, and then the mass ends up coming back to its original stretched position of 0.1. So that would be one complete revolution or cycle. So we've got the natural frequency of the oscillating system in revolutions per second, or hertz, also called cycles per second, and then 1 over that value would give us what's called the period of the oscillating system in seconds per revolution, or seconds per cycle. We use this value when we did some gravity examples, specifically the example of the Earth revolving around the Sun. Okay, so the time for one complete revolution is capital T. And we also used capital T when we were dealing with orbiting satellites. So if you're confused about that in any way, these terms apply to circular motion, simple harmonic motion, anything that's periodic and can be represented as kind of a circular or sine or cosine path. Okay, so these are important terms. You're going to see them in a lot of other classes. And for any given system, these are constant, provided that the amplitude and the angular frequency are constant, and that there's no damping. Okay, so here's an example problem that I'm going to go through for the rest of the presentation. We've got a mass spring system that has a natural frequency of 5 hertz, and that means that there's 5 complete revolutions every second. So let's count them, okay, so you get practice. And if you're interested in finding out how I know this has a frequency of 5 hertz, it's because I actually set it up in Excel to have 5 hertz frequency, and I posted the Excel spreadsheet with all of my work on Blackboard so that you can look at it, you can kind of tweak values and change it however you want so that it makes sense to you for other examples and for homework if necessary. So let's go through and count these complete revolutions and see, are there really 5 per second? So here's our 1 second mark shown in yellow, and we've got 1 cycle here, which is from peak to peak, 2 cycles, 3 cycles, 4, and then 5. So holy cow, we have 5 complete revolutions every second. Natural frequency 5 hertz. And so we can calculate the period, or the time for 1 cycle. And that's 1 over f, or 1 over 5, which gives us 0.2. So you can see drawn here that the time between wave peaks is 0.2 seconds. And so the angular frequency, which we really can't show on the picture, it's a calculated value, would be 2 pi radians per revolution times 5 revolutions per second, which is our frequency. And that gives us 31.4 radians per second. So omega is equal to 2 pi f, 31.4. And so the position of the mass at any time can be found using the equation. So what I did here is I plugged in amplitude 0.1, cosine omega t. So if you were to plug in any time into this equation, and assuming that you're dealing with your calculator in radian mode, so that's very, very important. We keep our calculator in radian mode for these problems. You would be able to determine what the position is of this mass at any given time, and it should line up perfectly with this graph. So try a couple values. Try, for instance, 0.35 seconds, 0.62 seconds, 1.3 seconds, for instance, and then see if you get values that make sense with this graph. We can also use our velocity and acceleration equations. So the velocity equation shown here, just plugging in values. We can determine how fast is this mass moving at any given time. So do that for a couple values. And you can actually plot velocity, and I do that in the Excel spreadsheet where I plot it so you can compare your values to the graph. And acceleration. So acceleration can be calculated using the equation shown. At any given time in the motion of this mass, you can say, hey, well, how fast is this mass accelerating? What is the direction of the acceleration? And that direction should always be toward the equilibrium point. So here is our velocity and position overlaid, and the right-hand axis shows the velocity in meters per second. The left-hand axis shows the position, and the green graph is the position graph, and the red graph is the velocity graph. And so you can see that these don't overlay. It looks like velocity is at a maximum point right around, let's see, so we've got right around a little after 0.1 seconds, which is before the maximum amplitude for the position. And it's actually when position is equal to the equilibrium point of 0. That's the maximum velocity, or the maximum kinetic energy. Makes sense because that's what keeps the spring moving forward. So it gets to the equilibrium point and it would ideally stop there, but instead it's got kinetic energy because it's moving due to the force of the spring that had already accelerated it. So hopefully that makes sense. You can see kind of where this velocity equals its maximum. Now obviously the velocity should be equal to 0 right at the end points of the motion, and that's what this shows, where it's changing direction. So we still have an acceleration, but we don't have positive or negative velocity there because the mass stops. So take a look at the Excel spreadsheet and go through some of this stuff and practice that way. Okay, so thank you very much for watching, and please be sure to go through example problems, go through the Excel spreadsheets, and let me know if you have any questions. Feel free to call me or email me with any questions you might have.